This module, Case Studies on BIM and Environmental Impact Integration, focuses on how building information modeling is applied across real-world projects to support sustainability, carbon reduction, energy efficiency, and climate-responsive design. The lecture emphasizes the practical and operational use of BIM throughout different stages of planning, design, construction, and building performance monitoring. While previous modules provided foundational knowledge and technical workflows, this module demonstrates the measurable environmental outcomes achieved when BIM tools, LCA platforms, energy simulations, and interoperability standards are used collectively. Each case study highlights the evolution of BIM from a digital modeling tool into a core environmental decision support system used by leading architectural and engineering teams around the world. This module begins with a short introduction clarifying why case studies provide essential learning for environmental planning. It then presents the evaluation framework used across all projects, including embodied carbon modeling, operational energy analysis, comfort simulations, and post-occupancy validation. Following the methodological foundation, the lecture examines 4 international case studies: Helsinki Central Library, Melbourne Council House 2, Oslo Airport expansion, and the Edge in Amsterdam. Each case is analyzed in terms of BIM workflow, tools used, environmental impacts, and design outcomes. The module concludes with a cross-case comparison, a set of best practices for BIM-enabled sustainability, and a summary synthesizing the shared lessons. The goal of this lecture is to strengthen students' understanding of how BIM supports real environmental outcomes in professional practice. By the end of the module, students will be able to identify how BIM-based LCA, energy modeling, comfort mapping, and procurement workflows operate in real projects. They will learn how various tools, Tally, One-Click LCA, Insight, Energy Plus, Radiance, Ladybug, were applied to different sustainability goals. They will also be able to compare how case-specific constraints shaped tool selection and data exchange strategies. Ultimately, students will be equipped to evaluate the strengths and limitations of BIM-based environmental workflows and integrate their insights into future planning and design tasks. Case studies offer an opportunity to understand how theoretical BIM workflows translate into actionable sustainability outcomes. While academic models provide a controlled perspective, real projects reveal the complexities of data integration, interdisciplinary collaboration, procurement constraints, and post-occupancy challenges. Case studies also illustrate how early-stage decisions based on BIM analysis can significantly influence the embodied and operational carbon footprint of a building. By examining completed projects, we learn not only which BIM tools were used but also why they were selected, how they influenced design choices, and what lessons were learned for future practice. This knowledge is essential for applying BIM holistically in sustainability-focused planning. Across all case studies, the same core environmental evaluation framework was applied, allowing for meaningful cross-case comparisons. Embodied carbon was assessed using LCA methodologies aligned with EN 15978 and ISO 14040-44 through platforms like Tally and One-Click LCA. Operational energy modeling was performed using Insight, Energy Plus, or Radiance to evaluate heating, cooling, lighting, and comfort performance. Material tracking and EPD matching supported accurate carbon accounting, while IFC or GBXML formats enabled reliable data exchange. Post-occupancy evaluation, where available, was used to validate accuracy, refine the model, and assess performance gaps. Together, these methods form a holistic framework linking design intent with environmental outcomes. The 4 case studies demonstrate a consistent use of BIM integrated tools, each designed to analyze specific environmental impacts. Tally and One-Click LCA were used to quantify embodied carbon, enabling material comparisons and scenario testing. Autodesk Insight and Green Building Studio supported early energy modeling and envelope optimization. For comfort, daylight, and solar radiation analyses, tools such as Radiance and Ladybug were applied. Data formats like IFC and GBXML facilitated interoperability between BIM software and performance simulation tools. These tools together illustrate a mature digital ecosystem capable of transforming building models into environmental intelligence systems. The Helsinki Central Library is a landmark public building designed with stringent environmental targets as part of Finland's national commitment to carbon neutrality. From the beginning, BIM played a central role in coordinating architectural, structural, and mechanical systems, allowing the project team to achieve transparency across design disciplines. The project team decided early in the process to integrate full LCA analysis into the BIM workflow so that embodied carbon could be measured before major design decisions were finalized. This early commitment to sustainability enabled the project to align its material use and operational performance with long-term environmental objectives. The project team used a detailed Revit model connected to Tally to conduct a comprehensive LCA during the design phase. Every significant material element, structure, facade systems, partition walls, finishes, was assigned environmental data from the Tally library. Several iterations were performed to compare structural options, glazing configurations, and insulation types. High-carbon materials such as reinforced concrete and aluminum were flagged through Tally's impact dashboards, allowing designers to test lower-impact alternatives. Operational energy data was integrated to extend the assessment beyond embodied emissions, resulting in a whole-life carbon view consistent with EN 15978 methodology. The workflow shows the power of real-time carbon feedback in complex public projects. The LCA revealed that structural steel and high-performance glazing were the largest contributors to embodied carbon. As a result, the design team introduced timber-based interior components and optimized the facade ratio to balance daylight with carbon considerations. Material substitutions reduced the embodied carbon significantly, aligning with Finland's national targets. The Tally-generated documentation supported transparent communication with municipal authorities and provided a carbon baseline for future refurbishment cycles. The Helsinki case demonstrates how BIM integrated LCA affects not only material selection but also architectural expression and lifecycle planning. Council House 2 in Melbourne is known as one of the earliest public buildings to fully embed passive environmental systems into its BIM-enabled design process. With an emphasis on comfort, natural ventilation, and biophilic strategies, CH2 sought to create a healthy indoor environment while significantly reducing operational energy demands. The building became a global reference point for how BIM can support the integration of innovative passive systems from early design through occupancy. BIM served as the coordination backbone for integrating passive design strategies such as thermal chimneys, night purge ventilation, automated louvers, and daylight-optimized facade geometries. Climate-based analysis tools, including Radiance and Energy Plus, were used to simulate daylight distribution, thermal loads, and seasonal comfort strategies. BIM's ability to represent both geometry and performance metadata made it possible to test complex interactions between building envelope, airflow, solar exposure, and occupant comfort. The iterative evaluation helped refine chimney heights, shading devices, and facade apertures, illustrating the value of detailed simulation in designing climate-responsive architecture. CH2 offers one of the clearest examples of the importance of linking BIM-based simulation to post-occupancy data. After the building was occupied, the operational performance did not match predicted energy savings. By comparing sensor data with the BIM model, the project team identified discrepancies in airflow behavior and adjusted the night purge system. This iterative refinement reduced the performance gap and improved comfort conditions. The CH2 case reinforces that environmental modeling is not a one-time task but a continuous cycle where BIM becomes a living model linked to actual building behavior. The Oslo Airport expansion project used BIM at a highly coordinated scale to manage structural complexity, material procurement, and sustainability compliance. The Norwegian government's emphasis on low-carbon public infrastructure required the project team to conduct extensive material impact analysis. To meet these requirements, BIM was used not only for geometric coordination but also as a central data repository for LCA and EPD-based procurement decisions. The entire airport model was exported via IFC into one-click LCA, enabling the assessment of steel, concrete, glazing, and other high-mass components that significantly influence embodied carbon. One-click LCA's automated EPD matching tools allowed the procurement team to compare different suppliers and materials based on verified environmental performance. The IFC workflow ensured data consistency across contractors and consultants. This case illustrates how BIM supports sustainable procurement by aligning digital material data with environmental impact datasets. The LCA highlighted opportunities to reduce embodied carbon through lower carbon concrete mixes and alternative steel suppliers. These findings directly influence the procurement process, demonstrating how BIM-linked LCA supports environmental transparency. The project achieved LEED certification, with BIM-based documentation playing a key role in energy, materials, and construction impact credits. The Oslo case exemplifies how BIM supports large-scale infrastructure projects where environmental accountability is essential. The Edge is widely recognized as one of the world's most energy-efficient office buildings and a pioneer in digital twin integration. The design team sought to create a building that not only minimized carbon and energy use but also continuously monitored its own performance. This ambitious goal required a BIM workflow deeply integrated with sensor networks, operational data streams, and advanced simulation tools. During design, BIM models were linked to insight and radiance simulations to optimize facade performance, daylight distribution, and shading strategies. The final digital twin integrates thousands of IoT sensors controlling lighting, temperature, and occupancy, with the BIM model serving as the central data interface. Renewable systems, including PV panels and geothermal heat pumps, were modeled in BIM-based energy workflows to estimate long-term performance and peak load reductions. This integration shows how BIM supports not only design but ongoing operational intelligence. The Edge achieved one of the highest BREEAM ratings globally, with operational energy use 70% lower than comparable buildings. The digital twin continues to optimize building systems, reducing energy use in real time. Occupancy-based lighting, adaptive ventilation, and detailed comfort mapping demonstrate how BIM-driven technology can create environmentally responsible workplaces. This case illustrates the future direction of BIM-enabled sustainability, continuous feedback, predictive modeling, and long-term performance optimization. Comparing the four cases reveals that BIM workflows differ depending on project goals. Helsinki prioritized embodied carbon. CH2 emphasized comfort and passive performance. Oslo focused on procurement and certification. The Edge represented a fully integrated digital twin model. Despite these differences, all projects shared three common factors: early adoption of BIM-based analysis, reliance on interoperable data exchange methods, and strong interdisciplinary coordination. These shared lessons highlight the flexibility of BIM as an environmental planning tool. The case studies show that environmental outcomes are strongest when BIM-based analysis begins early in the design process. Choosing the right tools, whether LCA-focused like Tally or One-Click, or energy-focused like Insight and Radiance, depends on project stage and performance objectives. Interoperability via IFC and GBXML ensures accurate data exchange, while post-occupancy evaluation validates design assumptions. These lessons reinforce the idea that environmental modeling is a continuous, iterative process rather than a single calculation. Based on the four cases, best practices include integrating LCA and energy modeling from the earliest design stages, matching BIM materials with verified EPDs, and using parametric simulations to explore multiple scenarios. Establishing a performance baseline early in the workflow enables efficient optimization. Finally, linking BIM to real-time building data creates opportunities for long-term carbon and energy management through digital twin frameworks. The four case studies demonstrate that BIM is far more than a modeling tool. It is an environmental intelligence platform capable of guiding design, procurement, and operational performance. Whether supporting embodied carbon reduction, passive system modeling, energy optimization, or digital twin development, BIM consistently enhances transparency and environmental accountability. These cases illustrate how data-driven planning leads to sustainable, resilient, and high-performing buildings across different contexts and scales.